Good afternoon again. Welcome to this Urban Model Seminar series. I hope everyone that wanted to join is joining. We're going to start now. So I want to thank you again for joining this, what is now the fourth session of this seminar. So it's called session 5 because we had to postpone session 4, but it's the fourth time that we're on air with you. So I'm Clémentine, and with my colleague Ruta, who's here today, Ali, who's not here today, but is working on the seminar with us from TU Delft. We're very happy to see you again to discuss, as usual, classical analytical urban models and their circulation. So once a month, and it's now the fourth time, an expert of urban studies and modeling dissects one model with a general question in mind. And this question is, what are the unforeseen consequences of urban model simplifications on our understanding of cities? So urban models are simplifications of reality, and these simplifications are modeling choices. They can be implicit or explicit, but what's interesting for us is that they have consequences on how we view, how we represent, and how we act on cities. So what we aim to do with this seminar series is to trace the discrepancy between models results and empirical analysis back to the model assumptions, back to the design choices. And the aim of all of this is to provide guidance on how to use models appropriately, knowing their the assumptions they rely on, but also to avoid misleading conclusions and ultimately to create better models for cities. So last year now, so last December, we had Jessie Lerousseau, who presented a talk about the unforeseen consequences of economic-based theory. The recording, if you couldn't attend, is now available on YouTube on the channel Urban Model Seminar. So we're also working at the moment with Ruta on editing those recordings into podcast episodes. So we'll let you know about these in the future. It's still in the making, but this is another way that we want to keep a legacy of those talks. But let me go straight to why you joined today, which is to hear Cécile Tannier talk about the fractal models of cities. So Cécile is a senior researcher in geography and planning at Théma Besançon in France. Her main areas of research are location dynamics in urban settings, the shape of cities, and the dynamic modeling of settlement systems. She's contributed to many research projects, many interdisciplinary research projects at the crossroads of geography, computer science, physics, ecology, economics, architecture, history, and archaeology. So a lot of projects which also have given rise to a lot of software applications that she's contributed to. So if you've heard about Fractalis, MobCity, Fractalopolis, Morpholim, Mobisim, Simfeudal, Artiscales, and Parcel Manager, I hope I said them well. I hope we will hear about some of them during her talk. Today, she will talk about fractals in general, the fractal model, and its impact on how urban forms and spatial organization are approached in urban studies and planning. She'll be reflecting critically on scale invariance and optimality, and show how and why fractal models enable us to better understand how space is organized through scales and how urban planning can modify this spatial organization in a fractal manner, accounting for the effects of distance and scale dependency. So as usual, she will have about 30-40 minutes to talk. Sorry, the audio doesn't seem to be, I'll try to, is that better for the person? The audio was a bit low. Okay. I hope it's fine, and I hope everyone can hear me fine. So I'm very pleased to hear Cécile today. So after her presentation, about 40 minutes, we'll open the floor to questions. Please use the chat for your questions. Ruta will be moderating the chat at the end, so asking your questions unless you specifically want to ask them. In that case, please notify her in the chat. And without further ado, I'm going to let Cécile talk about fractal and their impact on urban planning and urban studies. And she's talking to us from a nice location in the countryside. So over to you, Cécile.
Thank you, Clémentine. Thank you both, Rita and Clementine, for your invitation and for organizing this urban studies seminar series. So I will try and I will manage to share my screen just now.
Yes, we can see it.
Is it okay or not?
It's not full screen, but we can see the slides.
So I will try to stop sharing and put it full screen. I try another one more time. Here, can you see full screen?
Not full screen, but we can see a screen. Maybe if you want to zoom on the presentation.
And now?
Still not full screen. Ah, now it's fine. Yep, perfect.
Okay, so I can begin.
Thank you.
About this seminar about fractal models, scales, and urban planning. A first observation is that geographical shapes, in particular the spatial distribution of human settlements and the shape of cities, are highly irregular and heterogeneous. For instance, as shown on the screen, in suburban fringes of European cities, distances that separate buildings vary greatly. And similarly, when considering a whole city, the size of built clusters is highly variable, as well as the distances that separate them. In fact, many natural objects, such as coastlines, mountains, clouds, plants, cells, and so on, also have irregular shapes. Irregularity and complexity of shapes is the case in many domains of natural sciences, physics, biology, chemistry, and so on, and social sciences, finance, architecture, graphic arts, and geography, of course. Historically, mathematicians have let aside the study of irregular and complex shapes because such shapes could not be analyzed with classical mathematical tools. Infinitesimal calculus introduced by Newton and Leibniz during the 17th century is perfect to analyze smooth Euclidean shapes, cycles, rectangles, ellipses, but it is not appropriate to analyze complex and irregular shapes. Yet, since the end of years 1970, mathematicians have begun to systematically study such complex and irregular shapes. The most famous of these mathematicians is Benoît Mandelbrot, who is often called the father of fractals. And since the years 1980, all scientific domains have been considered in view of fractals. In geography, pioneering works have shown the interest of fractal analysis to characterize geographical shapes. Other pioneering works have argued that fractal dimension of real-world geographical objects is constant over a limited range of scales, but it varies over successive ranges of scales. Other contributions, specifically about urban geography, have explored the fractal aspects of area perimeter relations and the fractal boundary of urban forms. Since those, last but not least, others have discussed the scaling relationship between the number of built clusters and their size. And finally, other scholars have studied, shown that urban growth engenders fractal urban forms. Since all both pioneering works, geographers have always been interested in fractal analysis and fractal modeling. Evidence of this is the regular publications of numerous papers dedicated to this approach in renowned scientific journals. Euclidean geometrical figures such as triangles, circles, spheres, cylinders, and so on have only one characteristic scale. That's why when a part of the figure is enlarged, the whole figure cannot be recognized anymore. For instance, when zooming on one side of the triangle on the screen, we do not see a triangle anymore. We see a straight line. Similarly, the perimeter of a cycle becomes visually a straight line when viewed on a very large scale. In contrast, fractal objects do not have any characteristic scale. Each part of the object resembles the object as a whole. They are self-similar. As written by Mandelbrot, a fractal is a shape made of parts similar to the whole in some way. Moreover, fractal objects exhibit detailed structure over a large range of scales. They have a fine structure. Self-similar shapes have been invented a long time before the invention of fractal geometry, but few of them have been drawn before the computer era. I give you the most famous examples of those self-similar shapes invented during the 19th century. First, Carl Weierstrass has presented a curve that is continuous but not differentiable in all points. This is a mathematical object that cannot be drawn and seen easily. Then, Georges Cantor has proposed a self-similar set of points. And then, at the beginning of the 19th century, Helge Fraenkel has proposed a simple method to draw a continuous curve that has no tangent. Apart from the field of mathematics, other graphical representations of shapes that exhibit an internal hierarchy have been invented. Here you can see the geometric division of France in départements proposed during the time of French Revolution in 1989. Let me now show to you how to build a fractal shape. In fact, it is a Sierpinski carpet. The construction process begins with a simple figure that is called the initiator. Here it is a square. Then the generator of the figure is defined as a given number of reduced duplicates of the initiator. On the screen, the initiator is reduced by 1/3 and 8 duplicates are placed such that one square at the center of the generator remains empty. At the next step of the construction process, the generator is replicated into its 8 elements. The number of squares is then 64. The same process is reiterated successively. We can observe that the number of elements increases according to a multiplicative logic. 512 squares at the third step of the construction process. We can also observe, interestingly, that the gaps, that are the voids in the figure, are spatially distributed in a non-uniform way, and the relation between their number and their size is hierarchical. Thus, the geometrical scale dependence of the construction process of a fractal shape creates a self-similar shape. The Sierpinski carpet displayed before is strictly self-similar. its shape is exactly the same on all scales. I show you another example on the screen. However, real-world objects such as cities or coastlines are not strictly self-similar. They are statistically self-similar. Only numerical or statistical measures characterizing their shape are identical across scales. Consequently, their shape is approximatively but not exactly the same on different scales, as shown by these two figures. A statistically self-similar city, a theoretical city on the left, and a statistically real city on the right. An essential ingredient takes part in the creation of statistically self-similar objects, randomness. Randomness can be introduced very easily in the construction process of a fractal figure. Look at the example of the core curve presented previously. It is possible to place the peaks of the curve randomly upward or downward. And the random core curve thus obtained looks more real than does the non-random core curve. Let me give you now an overview of the interest of fractals for measuring geographical shapes. Because geographical shapes are highly irregular and complex, their quantitative description is very difficult. And very early on, geographers have noticed that density measures imperfectly characterize a spatial distribution or patterns. Such as the two images of Belgian communities that have the same built density, but that look like very different. This problem has been described by Mob Openshaw under the naming of modifiable areal unit problem. The states or the concentration measured depend on the size of the elementary spatial units, scaling problem, the shape and the positioning of the elementary spatial units, zoning problem, and the delimitation of the study area. In fact, the MOP covers a statistical problem shared by all natural and social sciences, namely the ecological fallacy. The first attempt to propose quantitative indices to measure the spatial concentration of population date from the first half of the 19th century. In France, concentration indices targeted the differentiation of two types of settlement patterns that are enclosed field systems associated with squattered settlement associated with squattered settlement, and open field systems associated with group settlements. Others have proposed to quantify the uneven spatial distribution of population via the measure of the deviations from a uniform spatial distribution. Later on, more complex methods of spatial point pattern analysis have been proposed. They consider the deviations from a random distribution that has the same density as the point pattern under consideration. Among those methods, the replace function is usually used. Those modern methods are based on neighborhood of varying sizes centered on each point of the pattern under consideration. And thus, several scales of analysis are introduced, and the MOP is limited to both the choice of a series of scales and to the spatial extent of the area under study. Let me now turn to fractal analysis method. No, I forgot this sentence. It is that finally, with all those classical spatial analysis methods, the spatial distribution adopted as reference, either uniform or random, is still too regular to characterize highly irregular shapes, in particular city shapes. Let me now turn to fractal analysis methods. I begin with the example of the polygonal line displayed on the screen. Its length, if I cover these lines with line segments of length L, the length of the curve of the polygonal line is 4 times L. Now, if I cover this curve with line segments of length 1/3 of L, the length of the polygonal line is still 4 times L. Now, I want to measure the length of the a core curve, which is a fractal curve, with this covering method. When covering this core curve with line segments of length L, the length of the core curve is 4 times L. Yet, if I use line segments of size 1/3 of L, the length of the curve is now 4 times 1/3 of L, thus lengthier than 4 times L. This illustrates the fact that the length of the curve, the fractal curve, increases as the length of the covering line segments decreases. Indeed, the size of a fractal object depends on the Turing measuring scale. And the fractal dimension has been invented to measure the size of such a fractal object, like the core curve, for instance. By definition, it is a non-integer measure. If an object is self-similar, it can be, at least statistically, it can be characterized by a power law that relates the number n of points counted within a spatial neighborhood of size epsilon, where d is the fractal dimension and a is a constant. In practice, the measurement process is as follows. It begins with counting the number of points of an object, centroid of buildings, black pixel of a binary image, intersection of roads, within neighborhoods of decreasing or decreasing size. Then one draws the curve that relates n and epsilon in a log-log plot. If this curve can be adjusted to a straight line, the slope of the straight line is the fractal dimension d. If the object under consideration is not statistically self-similar, the curve that relates log of n to log of epsilon is not a straight line, and d cannot be estimated. Yet, if the curve that relates log of n to log of epsilon is a straight line, this does not prove that the object is fractal. Different fractal dimensions can be estimated according to the way the neighborhood epsilon is defined and according to the scaling function chosen to obtain n. I have not enough time here to export them. Just to say a few words, fractal analysis methods usually used in human geography are the box counting analysis, the correlation analysis, the deletion analysis, the radial analysis, and the multifractal analysis. The different fractal dimensions obtained with these methods are not sensitive to the same types of spatial irregularities. Consequently, they characterize different aspects of a given spatial distribution. By definition, the fractal dimension of a two-dimensional object is comprised between 0, that is the topological dimension of a single point, and 2, the topological dimension of a two-dimensional surface. The fractal dimension of an uneven spatial distribution of dispersed points is higher than 0 but lower than 1. A smooth line has a fractal dimension equal to 1, thus equal to its topological dimension. A tortuous line has a fractal dimension higher than 1. Spatial or patterns that fill the two-dimensional space more than a smooth line have a fractal dimension comprised between 1 and 2. The fractal dimension is closer to 1.5 than to 2 when the gaps or the non-filled places are numerous and have different sizes. Finally, uniform build patterns, which may have very different density measures, have a fractal dimension equal to 2. A limit of the fractal dimension is that the same fractal dimension may characterize a large variety of shapes. Here, an example of a two-generator for which the fractal dimension D is equal to 1.46. In case of the generator A, the elements of the resulting fractal figure are connected, whereas in case of generator B, the resulting figure mixes connected and unconnected elements. Here, another example of two different fractal figures having the same dimension equals to 1.76. And again, another example of two fractal figures having a same dimension equal to 1.59. Those examples illustrate well that the fractal dimension says little about the orientation and the overall shape of the ultimate figure. Thereby, in order to fully characterize a self-similar shape, other properties have to be considered: the topological dimension, the ramification, the fractal dimension of the perimeter, and the lacularity, and so on. A small point about self-similarity versus scale invariance. Self-similarity and scale invariance both involve power laws. That's why some authors assimilate scale invariant functions to self-similarity or to fractality. Yet fractal objects are self-similar but not scale invariant stricto sensu. And conversely, numerous scale invariant functions are not fractal. A simplistic way to differentiate scale invariant functions from self-similar functions is to consider that fractal dimension is indeed the scaling exponent of a power law, but this power law is particular because it relates a number of elements n counting within a spatial neighborhood of increasing or decreasing size epsilon. So now I enter another part of my presentation that considers the fractal aspects of central place systems. Central place systems are common reference models for regional planning. A central place system is a set of centers, big cities, towns, small villages, that are of different sizes and that are organized hierarchically with respect to their commercial, administrative, cultural, and so on functions. The number of centers in each hierarchical level is all the more low that the level under consideration is high. Geometrical models of central place systems define the number and the spatial distribution of the centers. Centers are located the ones with respect to the others according to their level. The first graphical representations of central place systems have been proposed by Christaller in 1933 and Leuge in 1940. The basic geometrical figure is the hexagon that enables a uniform tiling of the plan in equal surfaces. Two examples are displayed on the screen. On the left, a central place system proposed by Christaller based on a market principle, and on the left, a crystallar central place system based on a transport principle. On page 65 of his book, Crystallar indicates the theoretical number of centers in each hierarchical level for his system based on a market principle in case of an area under study that contains 729 centers. As we see on the semi-logarithmic graph on the screen, the cumulative number of the centers in each level is a straight line. Indeed, the progression of the number of centers with respect to a descendant hierarchy of the centers is geometric. The multiplicative factor of this geometric progression is equal to 3. This statistical distribution of the number of centers with respect to the hierarchical level is thus scale invariant. Yet, in the general case, such scale invariance may exist or not. This depends on both the central place system under consideration and the spatial extent of the area to which it is applied. In this figure, for instance, the number of centers does not increase with respect to the level of the centers according to a constant geometric progression. Starting from the idea of a constant multiplicative progression of the number of centers with respect to a descending hierarchy, several authors have endeavored to demonstrate the fractal aspects of central place systems. Considering the Leusch central place systems, Arling-Gauss have shown that the boundaries of the nested market areas are fractal lines. For their own, Batty and Longley have suggested that self-similarity is directly invoked in central place theory. Yet, it is impossible to generate a central place system similar to those of Crystallar or Leusch using a fractal method. Actually, the patterns of Crystallar's or Leusch systems are intrinsically uniform and consequently non-fractal. Considering this, some scholars have proposed to spatially distribute the centers of a central place system following a fractal logic instead of a uniform logic. Chen has proposed to place a central place system close to that of Crystallar, based on a market principle, on a core snowflake. Interestingly, the number of centers within each hierarchical level differs from the number of centers in the Crystallar's figure, but it does increase according to a geometrical progression. Other scholars have proposed to build fractal central place systems. On the screen, you can see two hexagonal fractal systems that follow a deconcentrated concentration logic. The system displayed on the left is monofractal, which means that all elements in the fractal generator have the same size. In contrast, the system displayed on the right is multifractal. Interestingly, in this system, low-level centers exist only in the periphery of middle-level centers located far away from the main center. All central place systems presented before are perfectly ordered and regular. However, Izard has suggested to weaken the regularity of central place systems so as to become closer to real-world observed patterns. Actually, it is possible to vary the number of neighbors of each center either spatially or according to their hierarchical level. It is also possible to vary somewhat the distances that separate the centers without altering the scale invariance or the self-similarity of a system. Such variations have been introduced in the computer simulation model Fractalopolis that is dedicated to the creation of multifractal central place systems for urban and regional planning. Here on the screen, you can see an example of a multi-fractal development plan created with Fractalopolis for the urban region of Besançon in the east of France. The generator of the multifractal development plan contains two reduction factors. Consequently, the area of each center depends on its relative position. More precisely, it depends on the distance that separates the center from close centers belonging to higher hierarchical levels. Thus, the area of centers of different hierarchical levels can be identical, as shown by the two centers surrounded by blue lines on the screen. And concomitantly, the area of centers belonging to the same level can be different, as shown by the two centers surrounded by green lines on the screen. This property is not to be found in crystallars or luge central place systems. Yet, it tallies the empirical observation that centers of a same functional level are larger when they are located in the vicinity of a main center, whereas they are smaller when they are located in little populated areas. Besides, the multifractal development plan displayed on the screen is scale invariance as regards the hierarchy of the centers. This mention of the Fractalopolis model lets me to delve into the question of the interest of fractals for urban planning. A first sub-question is, does a good fractal dimension for urban planning exist? I have briefly mentioned previously that geometrical properties of different fractal shapes may strongly vary. Some fractal shapes are made up of connected elements across scales, as displayed on the screen. The elements of this fractal carpet are interconnected and actually form a single cluster. Other fractal shapes are made up of unconnected elements across scales. The example displayed on the screen is a fractal dust whose fractal dimension is 1.58. As you can see, the elements in a fractal dust form clusters separated by empty lanes of different sizes. A fractal dust contains just a few wide lanes and an increasing number of ever narrower lanes. The lane widths comply with a strict hierarchy. Other fractal shapes can be mixed both connected and unconnected elements. And cities in the world very often combine indeed features of fractal dust and fractal carpets. As you can see, the fractal dimension of the hybrid shape displayed on the screen is 1.58, just like the fractal dust presented previously. Interestingly, whatever the fractal dimension, the ratio between the size of the first largest cluster and the second, third, and so on largest clusters may vary a lot according to the shape under consideration. Thereby, a same value of fractal dimension can characterize very different shapes, and as a consequence, the question of the good fractal dimension falls de facto. No value of fractal dimension can serve as universal norm for urban planning. Now I move on to a second question about the optimality of fractal forms of cities. The discussion starts with the idea of self-organization. In a self-organized system, a meso or macroscopic order emerges from interactions at a microscopic level and constrains in return the future state and evolutions of the system. Starting from the idea that or the statement that a fractal order can emerge from self-organizing processes, fractality or multifractality is sometimes seen as a desirable equilibrium state. And subsequently, deviations from fractality can be seen as signs of dysfunction. Yet, these patterns frequently exhibit deviations from statistical self-similarity. And nevertheless, the syntheses under study are not all in decline, neither are they all dysfunctional. Adopting an organicist point of view, other scholars support the idea that urban planning should aim at the creation of fractal forms because such forms exist in nature in which they spontaneously emerge. Such forms are thus virtuous and optimal by nature, and fractals are raised to a universal aesthetic principle. Yet, adopting these viewpoints leads to most often to give more importance to emerging forms than to their generative mechanisms. Thus, resulting models are essentially structural. They take into account neither the real behaviors of individuals nor the strong emergence that characterizes social systems. In fact, a shape is not intrinsically optimal. It is optimal with regards to the processes, behaviors, practices that this shape allows to optimize. In case of human settlements, especially cities, the context, social, political, economic, natural, and so on, are highly diverse and change in the course of time. From this results a high diversity of human spatial behaviors and practices, and therefore possible optima regarding the shape of cities are not universal but context dependent. In a context-dependent framework, it is possible to assess the functional advantages of fractal shapes of cities with respect to non-fractal shapes. However, when attempting to do this, researchers encounter a huge difficulty, namely the fact that planning recommendations often contradict one another. For instance, a dense urban development may avert the loss of ecological habitats, but concomitantly increases the barrier effect of built areas to animal movement. Conversely, loose urban development increases landscape fragmentation, but the barrier effect of built areas to animal movement can be reduced. Therefore, functional advantages of fractal urban forms with respect to non-fractal forms are still poorly known, and the interest of fractals for urban and regional planning is not yet proven. Anyway, proving that fractals can help to achieve a sustainable development is very difficult, not because of fractal shapes themselves, but because a sustainable development involves numerous and diverse phenomena whose relations are very complex. The third and last question I would like to tackle is why incorporating fractal geometric rules in geographical models for urban and regional planning. The answer, as suggested, is that fractal geometric rules are interesting because they enable geographers to efficiently take into account both the effects of distance and the effects of scale dependence in their models. With regard to human settlements, scale dependence implies that the existence of a concentration process considering a certain neighborhood implies a dispersion process considering a wider or narrower neighborhood. The consequence of this is the modifiable areal unit problem mentioned previously. In particular, the level of detail of the representation of space, level of aggregation or spatial resolution influences the measurement of geographical shapes. Moreover, aggregation has a smoothing effect, which means that the concentrations measured are in general even strong, that the level of aggregation or the spatial resolution is coarse. Therefore, it is impossible to define a true population density at a point, since any estimate depends explicitly on the scale at which density is measured. Remarkably few geographical phenomena are scaleless. As we saw previously, a crucial property of fractal objects is that their size depends on the chosen measuring scale. Besides, the density of points in a fractal object decreases as the spatial resolution at which the object is represented becomes finer. This decrease in density is all the more marked when the fractal dimension is low. Ultimately, when the fractal dimension equals to 2, there is no decrease in density from one spatial resolution to the next one. Hence, the density of points of a fractal object is scale dependent, and this scale dependence is on a geometric nature. As for the effect of distance, they are twofold. The effect of distance can be first manifested in the form of a friction that reduces the mutual influence of phenomena as they move away. The distance can then be as much a kilometer distance as a cost distance or a time distance. Another effect of distance is that of belonging or not belonging to the same territory. The second effect partly explains the existence of spatial discontinuities or boundary effects. And the main consequence of the effects of distance is the well-known first law of geography. Elements close to each other are more likely to be related or similar than elements far away. With fractal geometric rules, distances between spatial entities are imposed more or less strictly at several nested scales. Thereby, fractal rules enable to efficiently take into account the effects of distance because they are intrinsically geometric and multiscale. By way of an illustration, I take the example of a fractal-based simulation model entitled MapCity. MapCity is dedicated to the simulation of different possible built developments, starting from a map, an initial spatial configuration that contains existing buildings, road networks, public transport stations, shop and services, green and recreational infrastructures. The simulation results are potentially interesting cells to organize whose size is 10 or 20 meter width in most applications made so far. The model does not integrate any temporal dynamics. Not only is the configuration obtained by simulation not located in time, but also the transition from the initial configuration to the simulated configuration is done in a single step, one shot. The new built developments simulated with MapCity are the result of the application of iterative geometric rules, which impose that an undeveloped space at a macro or mesoscopic level cannot be built at a microscopic level. MapCity thus preserves at a fine spatial resolution the undeveloped cells or spaces identified at a coarser spatial resolution. As a result, the simulated spatial configurations are statistically self-similar. The choice of a fractal dimension for the simulated developments imposes a certain spacing between the built cells and a certain form of connectivity between the undeveloped cells. Further to the application of the fractal rule of urbanization, additional accessibility rules are then used to select which cells to urbanize among the potentially developable ones. The overall evaluation of the interest of each cell to be urbanized is comprised between 0 and 1, with value 1 corresponding to the maximum evaluation value. Two examples of built developments simulated with MapCity are displayed on the screen. As you can see, in both examples, the simulated developments are visually realistic, even if the example at the bottom present a number of cells built by simulation much higher than in the case presented at the top of the screen. On this slide, you can see in more details that simulated forms of development are diverse. In the center, close to existing built patterns, the simulated developments correspond to an increased density of the existing built patterns, whereas at the periphery of the pattern, the simulated developments are under the form of new self-similar residential extensions. Another characteristic of MapCity is the possible variety of simulation results. They can first vary according to the position of the decomposition grid, as illustrated by the two examples of two positions of the decomposition grid, which leads to very different simulated built developments. The simulation results can also vary according to the random choice of the cells to be built in case of ex-aequo accessibility values. On this map, you can see the cartography, the mapping of 100 replications of the same simulation done with exactly the same MapCity rules. Cells in bright green have been selected in all replications of the same simulation. In contrast, cells in light green have been selected in only 50 replications upon 100. This variability of simulation results is interesting for planning purposes. Indeed, planners can choose among a series of maps simulated with the same set of MapCity rules regarding criteria others than those integrated in MapCity. So, to conclude this presentation, I would like to insist on the idea that fractal simulation models are interested for urban and regional planning, mainly because of their geometric and scale-dependent nature. Scale dependence can be introduced in fractal simulation models via the application of successive spatial decompositions respecting a principle of hierarchical nesting, as in the case of MapCity, or geometric transformations applied iteratively, as in the case of Fractalopolis. Thus, it is possible to explicitly take into account both spatial hierarchies and functional hierarchies. As for the effects of distance, with fractal geometric rules, distances that separate spatial entities created by simulation are imposed more or less strictly at several nested scales. So finally, the introduction of fractal geometric rules in the models enables geographers to better understand how space is organized through scales and how it is possible to modify this spatial organization while taking into account the effects of scale dependence and the effects of distance. Thank you for your attention.
Thank you very much, Cécile. And especially thank you very much for finding a solution to combine this seminar with your holiday and be with us today. And we are waiting for questions in the chat, so post some if you have. I will start with a comment, also a question. This is the fourth session of our series, and also the fourth urban model was presented. And those who have seen previous sessions have probably noticed that French names are mentioned very often. So, but still, could you comment on why the fractal model was born in the minds of French researchers?
Is it a question?
While the fractal model was born in France, if I understood correctly. You also mentioned other surnames, but if I understood well, the very initial ideas of this model was by French researchers, right?
In fact, the so-called father of fractals is Benoît Mandelbrot, who is Belgian.
Okay.
He came initially from Belgium, and he worked. He spent his infancy in Paris, but for his work, he was mainly at the MIT in the United States, and mathematicians other than Benoît Mandelbrot were not especially French. For instance, Falconer or Jan Stewart, they were not French mathematicians.
Okay, then sorry for my misunderstanding. I'm also curious, you talked about it, but I just want to maybe clarify a bit. You said that it's context dependent when you think of that some urban systems have more fractal structures than others. So it depends on the context where they are located, on environment, on social context, etc. And also, I know you said it's a bit understudied, but in your opinion, what could be the advantages of those cities or those urban systems that have more fractal structures?
It's not really my opinion. It's more assumptions or hypotheses that we are trying to confirm, but it's a work in progress. So our hypothesis, based on the study of theoretical figures, is that fractal cities enable a good articulation of built spaces with non-built spaces at all scales. So more concretely, a building, a residential building, can be close to a small green space, for instance, an individual garden or a small public park, and quite close to larger and larger spaces, larger parks, urban parks, and the peripheral green and natural areas and forests. Okay, it is the first advantages, assumed advantage based on the study of theoretical figures. The second is to create, to preserve the penetration of green alleys from the periphery, or green lanes, green alleys, quite large, not green corridors, not thin green corridors, but large green alleys from the periphery of the city into the center of the city, like in the finger plan of Copenhagen, it's an existing city, or the plan of Berlin. Okay. It's the second main advantage. And this preservation of green alleys supposes to refuse the creation of many circular large roads that boundary largely the city. So it creates a separation of the built spaces and built spaces to communicate the one with the others. People have to cross the center using public transport modes, transportation modes. So there are the three main advantages.
Okay.
Assume that it is.
Yeah, thank you very much for elaborating on this. And we have a few questions in the chat. So first, Denise, thank you very much for your question. And Cécile, you can also see them in the chat if it's easier for you to answer. But the question from Denise is, what do you think is more important for urban planning? Is it strict fractality, spatial nesting, or hierarchical organization of streets and centers?
Not strict fractality, of course, because strict fractal, strictly subsimilar figures are only a reference model to think about the possible organization of a city. But to my mind, it's not a concrete model useful to be applied in real cases. So the two important things are spatial nesting, but quite free, quite fuzzy, not strict spatial nesting, and hierarchical organization of streets and centers. The last two.
Yes, thank you. And then you have lots of greetings from Carlotta Fontana from the Politecnico di Milano. Maybe it's your friend. And then other question. Were there any attempts to understand the socioeconomic behavior that generates self-similar structures? For example, competition between individual developers, the shortage of information, etc. And there is a second question, maybe after the first one.
Okay. Several scholars have studied and reflected about the emergence of self-similar patterns based on the behaviors of individuals. And they have created for that models, behavioral models, that simulate the emergence of fractal patterns. In particular, Michael Batty and Longley have shown that the competition for the local competition for space can create self-similar shapes Other researchers, in particular Steinbeck and Pierre Frankhauser, and also, if I remember well, Nikos Salingaros and Geoffrey West have suggested that self-similarity can emerge from the joint occurrence of bottom-up competition processes and top-down planning and ordering principles processes. So some models are based on the idea of local and purely bottom-up self-organized emergence of fractal shapes based on competition processes mainly between individuals for competition for space, and other models are based on the combination of both bottom-up and top-down processes.
Okay, and one more question. How do you see the future works in fractal theory applications? Most of the papers were written in 80s and 90s, despite French and Chinese papers. It seems that fractality is not a very popular theme in urban science now. How could you comment on this?
So in geographical journals, indeed, quite few papers currently are currently published that deal with fractality of cities and so on. But in other types of journals, especially in statistical physics of cities, so the same topic, the same field of investigation that we geographers investigate, there are still a quite high number of papers that regularly appear and that deal with fractality of cities, of their build patterns, of settlement systems, of road networks, and so on. So I think that we have to distinguish fractal analysis and fractal modeling. In geography, at the moment, fractal modeling is not much developed, but it could be because of the strength of the fractal models to take into account scale effects and scale dependence. But perhaps it will take several years to develop and widespread. And on the side of fractal analysis, in contrast, I think that a huge work had been made until now, and that new improvements would be it's an opinion. It's not. I'm not sure of that, but I guess that new improvements will not be very interesting for improving our knowledge of geographical shapes of cities. But it's just an opinion.
Well, we need more of your opinions. If you know such models are context-specific and scale-dependent, how do we select the scale of geographic areas to conduct pattern analysis? For example, does it mean we can only select cities within the same country from the same period to compare the patterns as they would share the same government intervention and experience historical events?
No, of course, it is possible, and it is interesting to compare cities from different contexts. But we have to keep in mind that the mechanisms and the processes that have generated those different shapes may be or not the same according to the context.
Great. Clementine, would you like to add something?
I had a question of my own, yes, thank you. Thank you again, Cécile, for your talk. I was wondering, so in your presentation, it was quite clear that fractal models are very useful for urban studies, for studying cities, for describing urban form, for thinking about those models. But in terms of planning, I think your conclusion was really a lot more mixed. You said the interest was not proven. Do you think it can just be unnecessary, or can it even be harmful? And is it due, in your opinion, to a misunderstanding between the model assumptions and what it's used for, what planners might think it can do? Sorry, this question is a bit long.
I think I insist on the fact that the interest of fractals for urban planning is not proven because of a string of publications or ideas that mixes, that assimilate theoretical figures that have specific geometrical properties. First, some scholars assimilate such figures that are reference models to real-world cities. But the geometrical properties of those theoretical figures are not the same as the geometrical properties of real-world cities. This is the first thing. And second thing, few researchers have tried to compare the functional properties of theoretical figures, except Pierre Frankhauser. Almost no researcher have really compared the functional properties of theoretical figures. And a fortiori, even less researchers have tried to compare the functional advantages of real-world fractal shapes, realistic fractal shapes created by simulation. That's why I insist on this fact that fractals, the interest of fractals for geography is not proven, in order to erase some misunderstandings. But I hope that in the future, many young researchers will be interested in deepen our knowledge of the interest of fractals for urban planning.
Thanks. And maybe what I had in mind in this question is also, do you think, like, if you added fractals to planning mechanisms, could it be just the result could be harmful, or it's just it wouldn't do anything specific? Do you understand the...
No, I do not really understand.
Sorry, the question is, so you said that the interest for planning, until those comparisons are done and until we really know what the fractals can help, can do to planning operations, do you think it would just, if it was applied, if, for example, planners thought it was cool or nice to add fractals to their operations just because it's trendy, could it be just unnecessary and do nothing? Or could it also provoke some harm to cities that are planned that way because they wouldn't understand where it's coming from? I think you mentioned, for example, the competitions between animals and human access to different corridors.
I think that fractals, it's a model. Fractals to be used have to be included either into geometrical reference models or into simulation models. But both are models, and models can be well applied with intelligence, I don't know, and well interpreted, as well as they can be badly applied and interpreted. So it's a tool. It's a conceptual and a strong conceptual theoretical tool, but it is a tool for urban planning.
Okay. Okay. Yeah, I guess in this series we're trying to find what the tools, when used in a not optimal manner, can leave a trace in how we consider city or plan cities. So we're trying to find what the misunderstandings of the different models could have in terms of consequences on planning. But I guess it's harder probably with this one. So that's why I'm asking all those weird questions.
We have an addition from
Fractal models are in real case widely applied. We could answer you answer.
Maybe also have the comment in the chat that maybe the problem is who has the authority to decide the hierarchies in the cities and how planners can use it. That's the addition to your discussion. We have no more questions for now, and I think it's also time to finish today. And thank again very much to our speaker, Cécile, and all the attendants of this afternoon. And I will give Clementine the last words to announce what can we expect from the future.
Yes. Yes, I will just call for, if there's any last question, you can we still have 5 minutes. If not, I will invite everyone to join for our next session, which is in a month, exactly on the 7th of March. And we will receive Ron Boschma from Utrecht University about evolutionary economic geography. So I invite you to join us for that one. And if you want to replay this, you can always go back to our YouTube channel, Urban Model Seminar. And if that's it, I think there is no more questions. So I will wish everyone a very good afternoon and a very good week.
Thank
you for joining. Thank you for staying.
Thank you very much for joining.
Thank you very much.